Hi everybody, and welcome back to our fourth installment in our series, all about making intimidating maths more accessible. This time, we will explore a particularly notorious subject, vectors, their relationship to matrices, and more importantly, how these two fundamental concepts form the basic blocks of linear algebra. Firstly, a disclaimer before we start. Almost all research for this topic was taken from the fantastic 3 Blue 1 Brown series on the essence of linear algebra, as well as Zach Starr's informative videos on matrix applications, and I highly recommend you check them out. I'll explain less the actual theory behind vectors and matrices, but I'll provide the basic knowledge to understand some interesting applications regarding linear algebra later in the video. Firstly, what exactly are vectors? Well, there are two ways we can think of them, as a set of two values, the x and y coordinate, or as an arrow on the Cartesian plane. A useful way to think of vectors is as a linear combination of two basis vectors. This gives us a so-called foundation unit, or vector in this case, which we can use to express any other given vector in the same 2D space. We can choose virtually any two vectors as our two basis vectors, but for the purpose of simplicity, we will use the 1, 0 and 0, 1 vectors, known universally as the basis vectors in the horizontal and vertical direction respectively. Let's call them I hat and j hat. From there, we can treat each of the two coordinates of the given vector as scalar multipliers of I hat and j hat. So, if our given vector is 3, 5, it can also be expressed as a linear combination of 3, 1, 0 plus 5, 0, 1, or 3i plus 5j. What is the purpose of using basis vectors? Well, how we choose to represent vectors is based entirely on what we want the basis vector to be. The same vector can have completely different coordinates if they are represented as linear combinations of different basis vectors. Okay, so how does this tie into matrices at all? We have to think of matrices as basically a function that takes in vector inputs and produces vector outputs for each input. The transformation remains linear if and only if, geometrically speaking, the grid lines in the Cartesian plane remain parallel, evenly spaced, and the origin remains fixed. If we think of an arbitrary vector, xy, we can express it as x times I hat plus y times j hat. We can then use the given matrix and use it to transform the values of the basis vectors I hat and j hat. We can derive that the numbers on the left column will be where I hat lands, and the right column will be where j hat lands. Hence, xy will become x multiplied by the transformed I hat plus y multiplied by the transformed j hat, which equals to x 1, 4 plus y 3, 2. Therefore, we can be able to deduce the transformed vector based solely on finding where I hat and j hat is translated to. A two-dimensional linear transformation, or a 2 by 2 matrix, is solely described just by the two coordinates I hat lands on and the two coordinates j hat lands on. There are many more aspects that go into vectors and matrices, such as the concept of span, the determinant, eigenvectors, and inverse matrices, that I highly suggest you take the time to research on your own, after we go through some more neat characteristics regarding vectors and their relationships to matrices. A use of matrices is that they can help solve linear systems of equations. That is, there are no exponents, functions, or multiplying variables. Another requirement the system has to meet is that there are as many unknown variables as there are equations. We can group the constants into a matrix A, and the unknown variables into a vector x. When we multiply A by x, we get a vector that includes the solutions to each equation in the system, v. Geometrically speaking, we are looking for a vector x that lands on v after being transformed by A. Since we are looking for the unknowns, we want to find what matrix multiplied by v gives us x. Thankfully, we have a formula for that. We have to multiply v by the inverse of A. There is no such thing as dividing matrices, so we multiply matrices by their inverse, which gives us an identity matrix, which is basically 1. I will not go through how to derive the inverse of the matrix, as that basically involves applying a boring formula. Therefore, we can find the coordinates in vector x by multiplying both sides by A inverse, which basically gives us x equals to the inverse matrix of A multiplied by v. An even more interesting application of matrices is its usefulness in events that occur over a period of time. Imagine, if you can, a pandemic supervirus so contagious that certain cities go into lockdown and towns get quarantined. I know, hard to imagine. Now, there's a town in Pennsylvania, America, so heavily infected that the town is completely isolated from the outside world for risk of further infection. This means that no one can leave or enter, and the infection continues to ravage the town. Every day, 15% of the 1,200 healthy residents get infected, while 10% of the 300 infected recover. So, on the first day, the amount of healthy people would be 85% of 1,200 plus 0.1% of 300, which would give us 1,050. And the amount of infected people would be 15% of 1,200 plus 90% of 300, which would be 450. However, we are looking for the result in the long run, so we have to express these linear equations as the matrix of those percentages multiplied by the input vector h0 and I0, which is the current population of healthy and infected at the given day, which equals to the output hf and if, which is the population sizes at the end of the day. As we keep applying these multiplications, where will the output vector go? Well, this is where the eigenvector comes in. If you express each output vector as a vector on the xy coordinate plane, you will realize that after a long time, there will be a vector that will not change position after the transformation. If you place any vector on the xy plane and apply the same transformation, it will always move in the direction of the eigenvector. An eigenvector of a specific linear transformation is basically a non-zero vector that does not get pushed off the diagonal it is resting on when that specific linear transformation is applied to it. There are countless other uses of matrices, such as social networking, where you can express the number of relationships a certain person has in a matrix, and raising said matrix to a certain power can allow you to find the number of ways a path the length of the exponent you applied to the matrix can be made between a person to someone else. For example, cubing the matrix tells you how many paths of length 3 there are. To conclude, vectors and matrices play huge roles in being the main language by which we compute social networking, graphics design, robotics, or graphing out drawn-out events that, on the surface, seem to have no clear pattern. We really hope you enjoyed this introductory video to the beautiful world of linear algebra, and we encourage you to take it on yourself to look more in-depth into concepts you found interesting in this video. Thank you, and don't forget to smash like and subscribe, and click the bell icon for a free cookie. But not really.